The title of the slide gives it away. I think what we're going to learn about, but it's going to be running WebAssembly with WASI in Docker, which makes sense for where we are. So take it away.
Thank you. Can you hear me properly, or do I need to get better mic? All right. Hello, everyone. Thank you for coming. My name is Tibor Vass, and my colleague here is Tõnis Tiigi. We're two engineers on the Docker engine team. We're maintainers of Docker and maintainers also of a project called Buildkit, which is our next generation builder in Docker. And you might hear about it a little more. And today I want to talk about a little bit our journey with WebAssembly. But first, the question is why are two Docker engineers even interested in WebAssembly? And to answer that, let's first talk about a quick overview about what Docker is for those of you who don't know. So can I please get a quick show of hands of who has used Docker? Okay, so pretty much everyone. Well, so maybe for those who watch this recorded, I'm gonna just quickly summarize this as a platform where you can build, ship, and run any app anywhere. It's kind of simplistic, but sounds good, and I like it. So with Docker, basically, you can build safely any application. You package it all with all of your dependencies. You can deploy quickly the same application that what the author intended and run it in dev, test, and prod. And so you're guaranteed to run those same bits. And it runs in a sandboxed environment. And it's language and platform agnostic. So real quickly about Wasm, although previously Dan made a presentation about Wasm, and WASI as well. So I will go through this very quickly, but the main focus here is that WebAssembly is not only about web, it's also about non-web. In fact, I like to think about the web part of WebAssembly as just being as secure as JavaScript in the browser aspect. Because if you think about it, when you open a web page, it's more secure to open a web page than to download any binary and run it on your laptop. So if you're able to bring that level of sandboxing to the server, that's quite interesting and exciting. What we're more interested in is the other part, the sandboxing and basically the virtual ISA that Wasm is. So one great and exciting side effect of the fact that all the languages want to run in the browser is that all of a sudden you have a very low level common layer to all the languages, which is super exciting. So it's designed for portability and security, and it's a standard. Again, WASI, I'm going to go through this very quickly as well. You saw Dan's talk. So I'm not gonna stop in a lot of times. The main point I want to make here is it's the WASI announcement that got us interested in playing even with WebAssembly. That's the motivation here. So basically, when you didn't have Wasm alone, the hello world usually is just an add operation, so you can't do much apart from heating up a CPU, basically. So you need like host functions, which is described in the Wasm spec, and the problem is the browser has all sorts of host functions, and none of it is standardized. You can have your own, what we want is a portable aspect. And so if you no longer have portability, all those great aspects from Wasm are lost. So WASI is what guarantees, because if it's a standard, it guarantees that it will be portable. So if you have all those basically syscalls that where Wasm app can rely on. So quick recap is basically Wasm maintains the promise of portability and security. So if you're interested, you can probably contribute to WASI and put a link there. And now let's talk about the intersection of both. So how similar are Docker and Wasm? Well, the most tracking aspect is basically the sandbox and portability. We like to think of sandbox as basically an app that's isolated from other apps, and it's limited in what it can access. And portability is basically supposed to work the same on any machine. It's portable. So Docker and WebAssembly actually implement this very differently. Docker uses this concept of containers. Wasm has basically some guarantees in the spec. For portability, basically Docker has multi-platform images. It bundles the dependencies, and it's quite widespread now. It's super popular. And whereas Wasm has a universal binary, it's a standard. There's a 1.0 version, and I put a little exclamation mark here for modules for the future. So the great thing about sandbox and portability is if you have those two, you have an amazing property, which is you go from a situation but it works on my machine to you can basically build once and run anywhere, which is very nice. But Docker turns 6 years old, and it's extremely popular among developers. In fact, it's the #3 platform after Linux and Windows, according to this Stack Overflow survey of this year. And Wasm is relatively new, and WASI is like 2 months old, I think. So the obvious question here is how can we learn, basically? How can Docker help the Wasm community? And in order to answer that question, you can view through this lens of these three concepts of build, distribution, and runtime, which also is reflects the kind of workflow. So let's first talk about build in Docker. Whoops, sorry, I missed the. Basically, what my point here is when you want to build an application, you find, say, an open source project on GitHub, you download it, you want to build it, so you follow religiously those instructions. You have to cmake here, pip install there, and you have basically a failure. That happens relatively often, more often than we want to admit it. Yeah, in fact. My cousin just texted me this morning from Switzerland saying he's having a build problem and he's hitting some issues. So if you're watching, please listen. The core of the problem here is an inconsistent environment. You don't have the same environment depending on who's running it. So that's why you have these problems. So in order to avoid these, but it builds on my machine problems, Docker build basically allows you to build your application in a reliable way and safely without affecting your host. Like nothing changes on your host. And we have this file called a Dockerfile that's a quite simple way to describe your build graph, and it's language agnostic. It doesn't matter which language or build tool you use. Sorry. Clicking everywhere. There's a caching for faster dev workflow, and it's flexible. So again, for those of you who haven't seen a Docker file, I just want to quickly go through this. Basically, you have your source code somewhere in a folder. You have a Docker file. You explain what base image you start from. In this case, it's Ubuntu Bionic. You install all the dependencies you want with the correct versions. You put your code inside that container, you specify where you want to build, and you run the build commands. And the nice property of, you execute the build commands here by, you execute your Docker file here by running docker build, and dot to specify where all these files are. The nice property of this is that you basically, if I build this, I don't need to install anything in addition to it. All I need is Docker, and anybody else can do the same. So now let's talk about distribution. Again, I'm not going to go into too much detail here. My main point here is that we have an existing infrastructure with existing image formats, with configs and manifests and you can put your blobs, you can address your blobs in them, and all of this exists today. And one relevant point here is that we also support multi-platform images. In fact, I added Wasm right here just for this talk. So again, the main point is that Docker push and Docker pull, you can Docker push and Docker pull from a Docker registry, and it exists. It's been there for 6 years, and it's super popular. You have the Docker Hub registry, you have all the cloud vendors, and now even GitHub announced it, I think, last week. So if you want to create your own registry, go ahead. I put the link to the spec. Now, the runtime is basically containerd, which is a project donated to CNCF. So I put some links there. And specifically, if you were interested in Linux containers, runc is a reference implementation of the OCI spec. I also put a link here. So again, if you zoom out, this is the workflow of I build my application, I push it, and then I run it. Now, for the purpose of this talk, Wasm and the Wasm runtimes are basically all about the runtime. So I named a few that I know here, and let's look at build. So my point here is I want to talk a little more about the build aspect and the distribution aspect. So here, if we talk about build, how can we use Docker build to enhance the Wasm experience? So first of all, let's look at how you're building WASI apps without Docker. So imagine you have an awesome WASI app out there on GitHub. You read the README. There's maybe a requirements list. You install everything that's included there. Either there's a copy of what's today on wasi.dev, or it's just a pointer there. So you have to install all your build tools and dependencies, like CLang or Wasm SDK if you use the C parts of it, or if you are doing it Rust, then apparently you need Rust Nightly, if I'm correct. And all of these basically are things you install on your host, and depending on when you install it or how you configured it or what versions they are, they will differ from anybody else, and you'll run into those inconsistent environment issues that I talked earlier. You might even need to install other tools than just the things you need for WASI, such as Python or gRPC if you need to generate code. And again, different versions. So when you have a mutable environment, you have a higher risk of breaking changes. So, and that's exactly what Docker solves. So let's look at how we can solve this with Docker. You have a Docker file and basically a simple Hello World demo that I took from WASI. So you can specify again your base image, because in this case it's Debian. Put all your dependencies. You install all your dependencies. You download your the WASI SDK in this case. You extract it. You put your code in there, and you run CLang in this case. So that's the description of what you want to run, and you run it with Docker build up. Yeah, sorry. So one problem here is that basically I created an image, a Docker image, that contains my Wasm artifact. And if I'm on Linux AMD64, it's a Linux AMD64 image. So that's not great. I want to get back my Wasm file. So how can I do that? So where's my Wasm file? It's in the image. So here I basically just took the same Docker file and stripped it for more space. So what you can do in Docker 1903 is the following: is you can extract a build artifact specifically from the container, and you have it back on your host. The way you do this is the first original stage, you can call it the builder stage. You use that with the as builder, and then you create a second stage that you start from scratch, which means it's a completely empty container, and you copy the artifact that you wanted from the first builder container into this empty container. So in this, when this will build, it will build all of your all of the builder stage get the Wasm and then put that Wasm file into a Scratch container /. And when I build this, I can specify where to put all the contents of my final image. And here I just specify a directory called out. And when I run this, I see that in out I have my Wasm artifact. One little detail here that's important is I was assuming that you had enabled Buildkit, which you can do so on the daemon side as well. But for clarity here, I want to show as well how you can enable Buildkit on the client side in Docker. So it's an opt-in because it's the next generation builder. It's an opt-in feature. But for this specific use case of extracting a build artifact, you need Buildkit. And now I'll pass it on to Tõnis, who will talk to you about how to bring all of what I talked about in build further. Thank you.
So yeah, what Tibor showed you now is like how you can use Dockerfiles to build Wasm binaries, and that's all like really useful because like you get all those you get a workflow that's repeatable. But like in Docker, we don't really deal with binaries. We deal with applications. We build them into images, then we deploy them. So how can we do this? And the first thing to note about when approaching this is that Docker is multi-platform already. Like it started with Linux containers, and most people use Linux containers, but it also works on Windows. x86, of course, great support for ARM as well. And the way how we add this support in Docker is not that we like have like an ARM version of Docker and then ARM images in a separate silo. Like the way how we want to think about it is that you build an image, it should work from basically in all platforms. It should you should only work with like one artifact. And I guess the question in here is like how we can add Wasm and WASI into the same mix and make them basically the same thing as far as Docker is concerned. So the way you work with multi-platform builds in Docker or multi-platform images is that when you're running this Docker build that Tibor showed, there's a flag called --platform. And so you basically specify the platform there, what you want the end result to be. And that's how build will do the right thing. And this format that it takes is basically like defined by containerd. It's basically it's just like an OSN architecture. So if we look at like what it is for Wasm, then like Wasm is pretty clearly it's an architecture. Before WASI, we were like really lacking something to what to put in the OS. So now we can just like put WASI in the same place that we would normally use Linux or Windows, because WASI is really the thing that provides this syscall interface and is the API layer that the application is targeting. And as I told you before, what we also want to do is we want to create an image that should work like everywhere. So how do you do that? And like how do you build with for multiple platforms together? And before we get started on this, we need to mention those two projects that you need to use to do this workflows. One is Buildkit that was mentioned already. So this is the next generation builder toolkit that basically our newer version of Docker build is all based on. Comes with like lots of new features that you would want to use anyway, not even if you're like not interested about multi-platforms or not interested about Wasm. And the other project is BuildX that we launched just a couple of weeks ago at DockerCon. And what this is it's a Docker CLI plugin. So it like extends the capabilities of Docker CLI with some newer and modern build capabilities. Basically, like you can see, it does like a example of what Docker build will be in the future. And with those things in place, what you can do is you can do the regular Docker build, and with dashes, when you set the dashes platform, you just set multiple platforms together, just like comma separated format. And what we will do is we will basically take your Docker file and build it for both of them, then stitch them together, and you have the final image. So how does this even work? Like, how can you, like, normally when you run Docker build, you build for your current architecture only. So the way it works is actually like, there are different methods how we can make it work. One is just like a QEMU emulation that like ships together with our desktop products, for example. So when you get like Docker desktop on a Mac like this, there's support for like ARM emulation, for example, out of the box. So you can just work with ARM directly, and we will take care of all the configuration. You don't need to specify anything. Then we support distributed native nodes. So like you can just have two machines on different architectures, and the build will just separate the request out and build on both of them, then stitch them together afterwards. And for third, we have like pretty good support for cross-compilation straight in Dockerfiles. And basically, this is how we will approach the WASI applications. Like we would definitely need to cross-compile them. So before you saw how Tibor just had like a specific version of the compiler in the Docker file that generated Wasm binaries. But like now let's look at like how can we take this further and basically natively target the values that the user passes in with dashes platform. So to do that, what we do inside Dockerfile is that we expose a couple of special arguments there that are already there that you don't need to like define like you do with regular arguments, that are just filled in with correct values and that Docker will give you. So for example, in here, I have two stages in this Docker file, and the first one says that it's the image that is based on should come from a platform called Build platform. So what this means is that this stage is always the native platform for this machine that's doing the build. So for example, if I run this in here, it's like Linux x86. But when I'm running the CLang in here, then it is already seeing something called target platform in here. And what target platform is basically the value that you provide in dashes platform. So this is how your application itself can pick up what the value is, what the platform is that the user expects as an end result, and basically do the right thing. And I mean, it might be a little bit complicated because like CLang doesn't actually like understand this target platform value, for example, and there are other values as well. But for that problem, what we can do is we can just use a base image that already has all this magic built in. So for example, in here, I'm not building like an official like CLang image yet. I built actually my own image in here. And why I'm using this image is because this image already has all this cross-compilation logic in. This image can already see all those environment variables, these arguments that Docker will provide, and do the right thing. So in the end, I will just need to call CLang with the source file, and it will just do the right thing. It will either like build for my regular platform, or cross-compile to ARM, or cross-compile to Wasm. And yeah, basically that's what I just said. This is the repository where we have a couple of those base images that you can use for different languages. In cross-compilation, we have like images for Golang and C and now Wasm, of course, as well. So let's just take a look at this. So in action. So in here, I have just like a simple Hello World project. Let's make it a little bit bigger. And if I look at the Docker file, then it's actually the same Docker file that I already showed you in the slides. So it's a simple C Hello World application. What I'm doing in here is, again, like the first stage is my native platform. So this is where I'm running my CLang. I'm allowing the CLang to see this value, and just the CLang from this image in here will just do the right thing. For the second stage, I'm just like copying out whatever I built because like I don't want to have CLang in my final image and things like that. I'm just interested about the application. And if I just look at what the application itself is doing, then it's just like a basic hello world with some extra things that I just added in here to like a POSIX-like thing to just show like different features of WASI. So like I'm reading environment variables in here. Then in here, I'm just like looking at like what are the files in my root directory, then like writing a file, and then basically just like doing another read to see that if this file was added or not. So let's just take like little modification so we can see that this demo is actually live. And what we do now is like we just do Docker build. You can see that this is just like a regular Docker. I built an image. I can run it, and you can see that it just runs. This is just like a regular Docker workflow. So I'm running just like a regular Linux container, Linux AMD64. As you hear my files, like I'm writing a file and it appears in here. So just like regular Docker Linux AMD64 image. So now let's take this a little bit further. Let's try to build this multi-platform image instead. So I'm going to run basically the same build again. Let's give it a name as well. So let's do hello. And I have Dasher platform. And in here, let's do the AMD64. Let's do ARM one as well, just for fun. And let's do the Wasm that we're here about. And I also want to just push this image straight into the registry because like if you're building multi-platform images, you want them to be locatable from different machines. So and I'm missing a dot in here. So this one builds. I had the cache for the image, luckily, but the build, you can see like the different invocations in here. You can see that the CLang was actually invoked like 3 times in here. So these are all the separate compilations for every architecture. Then it finishes up. It creates all those distribution objects. In the end, it creates this thing called manifest list. That's like the multi-platform image. And in the end, it pushes this all into registry as well. So you can just inspect it right away. So index tools inspect. And so I'm just inspecting this image that I just pushed to the hub, straight from the hub. And I see that this image is for 3 architectures. So this is the AMD64 ARM. And you can see that there's like a WASI image in here now. And this is straight in the hub, like there's no like special source or anything in here. Like it works with all the current architecture. So let's try to run it. I already let's do the thing that I already did before, Docker run, not hello, but hello. And see that this is the Linux AMD64 image like before. I should have an ARM machine as well in here. So this is just an ARM node. So let's do the same thing in here, Docker run. And so in the ARM node, it will look for the same multi-platform image, but in the end, it will pull only the ARM version of it. So only the ARM submanifest, only the ARM binary. But it runs exactly the same as you would expect in like running Docker containers. So it's the same thing, only the platform in here now is ARM64, not the AMD64. So, but let's look back for this inspect and then like try to figure out like how can we run this thing now. And to run this thing, well, you can't run it out of the box, right? Because out of the box, what Docker will do is it will try to run a Linux container, and this definitely is not a Linux container. This is the same distribution format, but the actual binary is a Wasm binary. So, but Docker already supports different type of runtimes that it can use to actually invoking the resource. And the way it works in Docker is that Docker is based on containerd, and containerd also has this logic. So, and containerd has this shim API that can be used to, for example, for other people to create their own versions of a shim, and then they can run different types of payloads. Like this is, for example, like how Kata containers work, or Gvisor, and all the different formats that you can also run with containerd and Docker. So, so what we need basically to run this with containerd is to have a Wasm shim, and luckily there was just a repository made today that has this capability. So 2 hours. Yeah, it's really 2 hours ago, and because of that, I need to show it through containerd, so it doesn't quite yet work through Docker. I saw it working through Docker as well today, but it needed a little bit of hacks to do that. So, but let's show this in containerd itself. So containerd itself comes with a CTR tool, and it's like a little bit not as user friendly as Docker. So I need to use this cheat sheet to figure it out. But basically what I'm doing is I'm doing like image pool in here. The CTR, when I'm doing the pool, I need to specify a platform. In this case, it's Wasm, and I'm building the same image that I just built. So this one is just doing the image pool. And now let's try to run this with a CTR run. So this is CTR run. I need to specify the runtime. So this is the runtime, how it picks up the different shim API. And this is, I need to specify the platform again and image, and this is just an ID. And you can see it was really fast, and it works fine. So it says the same thing, hello Wasm, and now it recognizes that it is Wasm. And you can see that the rest of the things are exactly the same. So before I only had my binary in my root directory, then I'm writing a file foo, and the foo appears in here, exactly the same like secure sandbox experience that you would have in regular Docker. Thank you. So this was through containerd, and pretty sure it will soon be like this through Docker as well. But so this is very cool if you, for example, want to schedule Linux containers and Wasm side by side, for example, and I know use them through Kubernetes, things like that. But it's maybe a little bit heavy in some use cases for Wasm, because there's lots of things to set up. For Wasm, we don't really we can just run it as a random unprivileged user, so we don't really need the daemon and containerd and all this for all the use cases. So for that one, there's this demo application called Docker Wasm. That's basically it's just a demo application that has a simple Docker-like experience, but works directly with those Wasm images that I just built. And what's cool thing about this is because Wasm works basically everywhere, then this terminal in here, I'm running this in OS X, so actually natively in this laptop. And this is something that we can't do in containers, for example, because Docker can't run containers natively on macOS. Even if you use Docker desktop on a Mac, it's actually like running Linux in a VM. So, but in here, see what actions I have in here. I have ls to list images, and I have pool. So let's just try to run it. So I built hello. And what happened here? I just pulled the layers. It was exactly the same as you saw in the other the container demos. Pull those layers and run the same application that I just built directly on macOS, and basically it runs in anywhere where just with the help of a Wasm runtime, and you can just run it again, and you can work on with images and stuff like that. So the way this works is that we pull down the layers using all the Docker standards and Docker utilities, and then we invoke it with a runtime that already exists. So in this case, for WASI, we are actually, like in the end, we are invoking it through the Wasm time runtime. I've tested this with Wasmer as well, works fine in there as well. So we can just make it optional. And what you can also see is that because WASI is safe, that this thing in here behaves like totally like a container. So when you're doing the open-tier of root in here, you're even in OS X, you're like actually in this sandbox environment that's very similar to Docker container. You don't have access to like this application, although it can open files, it can like work with files, it can do like some crazy things. It's all still sandbox in this container that either Docker or this tool will provide it. And let's do a little recap. So what you saw is we built an image live for all those three architectures, push to live registry, push to hub, and we can run this image on any platform. Wasm is just a first-class platform like any other that we currently are supporting, and this is all like live. You can start building your own images with Docker and push them today. Like it works out of the box at the moment, and it didn't require like absolutely no changes in Docker code for build and distribution part. So build and distribution part is like there's nothing Wasm specific or anything like this there at all. And for the run part, like I mentioned before, there's this container shim project now next to Derek that you can find it from this URL. So if you compile this, you can use it with containerd to run those Wasm images today by specifying this runtime flag. And the plugin that I showed is in this address. You can just get it, and this runs on like any platform as an unprivileged user, no dependency on Docker or anything like this, and is like fine-tuned for Wasm only. So it will recognize, it will only pull Wasm image out of the box and things like that. And with that, I'm passing it back to Tibor.
Thanks, Tõnis. That was a pretty cool demo. So actually, when WASI was announced, Docker founder Salman Hikes tweeted this. It's a tweet about how basically Docker and Wasm could integrate fairly well and would run Linux containers and Windows containers and Wasm containers side by side, essentially. And I just find it really cool that basically the demos you saw today basically fulfill this. So that was just about it. I want to talk just a quick point about differences in portability between Docker and Wasm. Both are portable, but in actually a different way. When we talk about portability in Wasm, we mean that the binary itself is universal. It's portable. You can run it anywhere where you have the Wasm runtime running. But in Docker, basically, when your app is portable, it means that it includes all its dependencies and environment and files, dependencies, etc. So I just want to point out that whatever is the future of the Wasm spec around modules and importing modules, I'm a little bit wary about the potential dependency hell that might ensue there. So just to keep that in mind. A couple of discussion topics or future work or topics to chat after. It would be interesting to think also about the process model, like how would WASI implement fork? I'm sure Dan has thought a lot about that as well, but this would allow us to basically implement a Docker exec, which in the Linux world executes a process in the same sandbox that an existing container is. And so although the processes are separate and like they all have their own memory, the file systems are shared and the network resources and all that. So how would fork work? Would that be, you would create a separate instance of a Wasm? Anyway, so that's up for discussion. And I want to talk also about bin format, or binfmt, I don't know how you pronounce it. It's a not often known thing in Linux. It's basically what Docker for desktop uses to set up QEMU as the default ARM emulation for an ARM binary. So basically what this means is that when your system finds an ARM binary on an x86 machine, it goes through this bin format registration step, and it's like, oh, I recognize this is an ARM binary. Let me invoke this command and run it through QEMU. So we could do the same thing with Wasm. You could have like the Wasm on a machine, and if you set up the bin format registration properly, then it could invoke your favorite Wasm runtime to run that. So that could be pretty cool. On the distribution side, it's also very interesting to think about, instead of JIT Wasm runtimes, to think about ahead of time Wasm compilers in that build ship run workflow. Well, mainly the build ship part. So if you think of the registry storing the Wasm artifacts, the Wasm bits, instead of sending the Wasm bits to the client that requests the Wasm payload, the Wasm app, the registry could be a little smarter and recognize that the client is, say, actually a Linux MD64, and then compile on the fly. And if it has it in cache already, then serve that. But the point is, it would compile on the fly the Wasm application to the native Linux MD64 with the similar guarantees. Another aspect where you could put the ahead of time compiler is if you wanted to, instead of getting it at pull, making that at push. So essentially, when you build your image and you push it to the registry, instead of pushing a Wasm app with Wasm bits, you push all the different architectures that it compiles to from Wasm. Yeah, and another interesting thought here is a cool hack that we didn't succeed in doing, but essentially is to think of what could a Linux/Wasm platform look like. So there's basically two ways: is you port Linux to Wasm. So good luck with that. Another interesting way is we've been quite interested in this Google project, open source project called Gvisor. It's basically a Linux user space implementation of Linux in Go. So that's interesting. And it allows you to basically, their main use case is essentially to isolate the host kernel from your containers, because regular Linux containers essentially share the same kernel. And if you put a user space kernel in between, it's basically another level of security. But we could use those bits of Gvisor to essentially use the sandboxing, to use that as a sandboxing mechanism for the Wasm runtime. So the problem is that Gvisor is 64-bit, and Wasm is 2-bit, so you would need to try to port Gvisor to 32 bits, and looking at the code, there's a lot of 64-bit assumptions. Another way is to instead try to see what the Wasm 64 state is, and I didn't manage to get muzzle compile with Wasm 64, but I don't know, maybe someone can help me. So because Gvisor is in Go, we would need to have like a Go Wasm runtime to integrate with. Basically, when you want to like do memory operations, to use the Gvisor's memory primitives. And yeah, so that's just a couple of cool ideas. And yeah, just put a couple of links here for the various things we talked about. And yeah, just a note that we're hiring. So if you're interested, feel free to contact us. And thank you very much. We're open for questions.
So we have time for some questions before, we have about until 8:20, 8:30 before we get kicked out. So let's use that time.
So I was really excited to hear about the fact that you can now extract artifacts out of a Docker image. But that sounds great for static binaries. But how does it play with the fact that sometimes you might need like additional dependencies other than just like an artifact, maybe like some .so files, for like, a Linux thing that you're trying to build. So is there any way to like extract additional like platform specific files or libraries as a part of the artifact?
So if I understand the question correctly, you're saying here, I don't want to just extract my demo.wasm artifact. I want anything that it needs, that it depends on if we have maybe Wasm modules and maybe all the other modules that it depends on, etc. So what you would need to do in this workflow would be to add more of those files, like after appdemo.wasm, before the slash, you would add more of those, or multiple copy --from equals builder lines, and basically you put everything.
The entire thing.
Yeah, it's much easier if all of it is already in a folder in your previous stage. That way you just have one line where you put that folder in, yeah.
I had another question. At the very end, you mentioned about the experimenting with the ahead of time compiler. Experimenting with the ahead of time compiler.
Yeah.
Have you played around with this thing that Fastly recently open sourced, Lucet?
I haven't played extensively with it, but I've tried it when it was announced, yeah. Any other questions? To me or to Tõnis, by the way?
Builder X stuff, does that work with Docker for desktop?
I'm sorry, what?
Does it work with Docker for desktop on the Mac?
The first part.
Buildx.
Oh, Buildx.
Builder X.
So Buildx is one part of it is that it's like a CLI plugin, so that like it extends Docker itself. Like you get like, as you saw, I run Docker Buildx, and this is a new feature that like CLI plugins is a new feature in Docker, like the release that's currently in beta. So it will be in the next release. Or as a standalone, you can just use it directly, and you can basically use it in like with any Docker version as well. Like you can just.
Yeah, it even works with older versions.
Yeah.
Any more questions? No? All right.
All right, another round of applause. Cool. So it's 8:04, 8:05. We can stick around for another 20, 25 minutes as we tidy up. Feel free to socialize, talk to the speakers, and just another plug for next month's meetup at Google, June 25th over at Spear. So if you're interested in